finite section method is the probably simplest, but already fairly instructive, example of a very large class of approximation methods, the so-called projection methods. Let's quickly recall the setting of the finite section method and then try to generalize. Okay, so at first there's our operator A between the spaces x and y. And then you start to look at typically finite dimensional subspaces xn of x and yn of y. For the FSM, x and y are typically sequence spaces, so the elements are infinite vectors, if you want to say so. So let's take two different LP spaces here. And the subspace xn here consists of those infinite vectors from x that are only supported on the first n components. And you do exactly the same for the subspace yn of y. And then we have these projections Pn that take an infinite vector from x and truncate it so that only the first n components remain and the rest becomes 0. So that your space xn is just the image of that projector Pn. And then the same kind of truncation is also happening on the other side, where you take infinite vectors from y and truncate them to elements of yn, where only the first n components remain and the rest is replaced by zeros. So formally these are just the same as you write here, but you have to give them different names because the operators act on another space, on a potentially different space y. So let's write essentially the same thing here, only that now Pn hat, as we call it, goes from y to y. And in fact, the images are always in yn, and yn is exactly the image, so the set of all outputs of Pn hat. Okay, and in the same style we would say that this Pn here is going from capital X to capital X. Right, so much about the finite section method. Now let's try to get some inspiration from this and understand how we should create our new projection methods. So let us start with a general projection, Pn from x to x. And let's introduce this much more general subspace xn here as the image of that projection Pn, very much in the style like we had it here. Okay, and then you do completely the same thing on the other side, and because y could be a very different space, you have different projections here. And also here you define your subspace yn as the image of that other projection. Okay, and then someone gives you a right-hand side b and asks you to solve the equation ax equals b for x. And because we want to break down things to these subspaces xn and yn, you want to get your b down to this one of these subspaces yn, which it usually isn't in already because, well, in our FSM example, this would mean you get a right-hand side that is only supported on the first n components. Okay, but because yn is just the image of that projection Pn hat, let's apply Pn hat to our right-hand side b, and that of course brings you into your subspace yn. Now, instead of aiming for b starting from somewhere over here in x, you're now aiming for this new point Pn hat b, starting from somewhere over here in x. Or even better, you want to start in this subspace xn, because you only want to work on these subspaces xn and yn. So while here the problem was to find a solution x in x for which the equation holds, now the new problem is to find xn in the subspace xn such that axn equals this projected right hand side Pn hat b, which is already in the subspace Yn. Okay, but then starting from somewhere here, let's say little xn in capital Xn, there is no reason to assume that the image of that point is automatically in the subspace Yn, because your subspaces xn and yn naturally have nothing to do with the operator A, so there's no reason why elements from xn should be mapped over to elements in yn. All you know is that, well, they end up somewhere in y, because you start somewhere in x. And the best thing you can hope for is that only after projecting it down to yn, you end up at the same point as P was ending up when being projected down. So we see that in general we cannot make this true only if we add Pn hat in front here. Now at this point, let's again recall our finite section method, where the equation was looking roughly like this. Well, let's just check back what we did there. Okay, well, maybe for this particular example of the forward shift operator A. So we started with this infinite vector x. We projected it down to the subspace capital Xn, where vectors are only supported between entries number minus n and n, which are marked by these black bars here and here. Then your operator A comes in and brings you to the other side from xn to, well, not yet yn. First you're in capital Y, because you can see there's at least one entry outside the black bar, so you're not yet in yn, but of course this projection brings you down to yn, and there you are. If you see the whole composition, it's looking like this. You have Pn, A, Pn, and in our new more general setting we would place a hat on top of this Pn, because this is now on the other side where the spaces are called Y and Yn. Still in our equation for the new more general projection methods, we didn't see this Pn coming, this one here, because we started from an element of the subspace xn, which would be here. But in any case, it doesn't hurt to apply the operator Pn again to that element. It wouldn't change the element because, well, you can see it's the image under Pn of some vector, and if you apply Pn again, then Pn being a projector doesn't change the result anymore. So even if you start with an x from the subspace capital Xn, you can still squeeze this projector Pn in here without any consequences. So let's do that. Okay. So in our case, we would squeeze Pn in here, noting that this here is of course still xn. But in theory you could apply this composition here of Pn A and Pn hat to an element that's in capital X, not the subspace Xn, and this projection Pn would still bring you down to capital Xn. And here we are in our setting of an approximation method. So this is the operator an, and this is the right hand side bn, and of course here we are looking for the solution, but now only in the subspace xn. Okay, well, up here we claim that we get a particular class of approximation methods, and for this to be true we need the following. We need that an goes to A strongly and bn goes to B in the norm of your space Y. Let's start with the second question. Well, bn was just our abbreviation for this expression here, pn hat B. And we need this to converge to B for every right hand side in our space Y. But in operator language, this expression here means nothing but pn hat converges strongly to the identity operator, because you can of course squeeze the identity in here without changing the meaning. So let's add this to our assumptions that we have to make at the very beginning. And for similar reasons, because these elements xn, which are coming from capital Xn, shall converge to our proper solution x, which could be anywhere in x, we will need the same condition also on the other side for these projections here. And to avoid confusions, we should say that this is the identity on a space x, and this is the identity on our space y. Okay, but then we can tick this question here, and we are left with that one. Okay, and to answer this one, we of course have to recall what an is by our definition. And then it's fairly tempting to use the following argument. You say, well, this Pn converges by our assumption to the identity on X, and this Pn hat converges by our assumption to the identity on Y, and this A remains in the middle unchanged. So the limit of that product should just be the product of the limits, because we are used to this rule from sequences of numbers or even slightly more complicated things, but we don't have a proof yet for operators and strong convergence. So this is what we need next.